What if everything you see, touch, and experience isn't real? What if the universe around you, the stars, the planets, even your own body, is nothing more than an intricate illusion, a cosmic hologram projected from the edges of space-time? This isn't the plot of a sci-fi movie. It's one of the most mind-bending ideas in modern physics, the holographic principle. Imagine peeling back the layers of reality only to discover that our three-dimensional world might just be a two-dimensional shadow, a flickering image on some unimaginably distant surface. It sounds impossible, yet some of the brightest minds in science have spent decades chasing this very possibility. The holographic principle emerged from the collision of two seemingly incompatible pillars of physics: quantum mechanics and general relativity. In the 1990s, theoretical physicists like Leonard Susskind and Gerard T. Hooft proposed a radical solution to one of the universe's deepest mysteries: how to reconcile the behavior of black holes with the laws of quantum physics. Their answer: the information that makes up our reality might not be stored within the volume of space itself, but encoded on its boundary like a cosmic DVD. Picture this: everything you've ever known could be nothing more than data etched onto the fabric of the universe's outermost edge, projected inward to create the illusion of depth, of substance, of life. This video is your gateway into that astonishing possibility. We're about to dive into 30 theories that explore the holographic nature of our universe, each one more fascinating than the last. From the idea that black holes are cosmic projectors to the notion that time itself might be an emergent property of this grand illusion, we'll unravel the science, the speculation, and the sheer wonder behind these concepts. Whether you're a seasoned science enthusiast or just someone who loves to ponder the big questions, this journey will challenge everything you think you know about reality. So buckle up. By the time we're done, you might never look at the world or yourself the same way again. At the heart of this cosmic mystery lies a revolutionary idea: the holographic principle. Think of it like the security hologram on your credit card. From one angle, it's a flat, shimmering sticker, but tilt it just right, and suddenly you see depth, layers, even movement, a three-dimensional illusion emerging from a two-dimensional surface. Now scale that up to the size of the universe. What if every star, every galaxy, even your own thoughts, are just projections from a vast, hidden surface at the edge of reality? This isn't just wild speculation. It began with a paradox about black holes. When matter vanishes into a black hole, what happens to the information it carried? Quantum mechanics insists information can't be destroyed, yet black holes seem to erase it. Leonard Susskind and others proposed a solution: the information isn't lost. Instead, it's smeared across the black hole's event horizon, the point of no return, like invisible ink on a cosmic ledger. Over time, this idea expanded. Maybe everything in the universe works this way. The three-dimensional world we experience could be a projection from a vast, two-dimensional boundary we can't see. The math behind this is dizzying, but one key clue comes from something called the AD/CFT correspondence. Imagine a can of soup. The soup inside, thick, complex, full of ingredients, represents our universe. But all the information needed to make that soup might be written on the label wrapped around the can. That's the core idea: a higher dimensional reality encoded perfectly on a lower dimensional surface. Why does this matter? Because it suggests that space itself, the very stage on which the universe plays out, might be an emergent property, not fundamental. Like the pixels on your screen creating the illusion of a continuous image, what we perceive as solid and real could be built from something far stranger. The holographic principle doesn't just challenge how we see the universe, it rewrites what we think reality even is. The idea that our universe might be a cosmic projection flips reality as we know it inside out. Picture standing in front of a giant movie screen, except instead of watching a flat image, You could step into it, feeling the warmth of the sun, the weight of objects, even the sting of a scraped knee. That's the essence of the holographic principle, a three-dimensional world emerging from a two-dimensional source. Juan Maldacena's groundbreaking paper in 1997 gave this wild idea mathematical muscle. He showed how a hypothetical universe with specific properties, think of it as a warped, gravity-filled space, could perfectly correspond to a simpler, flat universe without gravity at all. The equations matched, like translating a novel into another language without losing a single nuance. To grasp how this works, look at an ordinary hologram. Shine a laser on a flat, etched surface, and suddenly, a three-dimensional bird seems to hover in mid-air. The depth, the shadows, the way it shifts as you move, all of it comes from information packed onto that flat sheet. Now stretch this concept to cosmic scales. The universe's boundary, if it even has one, could hold all the data needed to generate every galaxy, every particle, every fleeting thought inside your mind. We're not just talking about a visual trick. The math suggests that time, gravity, even causality might be secondary features, emergent from something far more fundamental. Maldacena's work was like finding a secret key. Physicists had been wrestling with how to unite quantum mechanics and gravity for decades. His discovery hinted that gravity in our three-dimensional world might just be a shadow of quantum interactions playing out on a distant two-dimensional surface. Imagine a puppet show where the strings are invisible and the stage itself is an illusion. That's the level of cosmic sleight of hand we're dealing with here. But how could this possibly be tested? Enter black holes again. These cosmic traps don't just bend space, they stretch the holographic idea to its limits. Calculations show that the maximum entropy, the disorder or information, a region of space can hold doesn't depend on its volume but on its surface area. It's as if the universe is telling us what matters isn't what's inside the box but the wrapping paper on the outside. Experiments with quantum computers are even trying to simulate these holographic connections, searching for glitches in the cosmic code that might reveal the projection behind the curtain. This isn't just about rewriting textbooks. If the holographic principle holds, it means reality is a kind of structured hallucination, a shared dream etched onto the farthest edges of existence. The chair you're sitting on, the device in your hand, none of it is solid in the way we assume. Instead, everything is a dynamic interplay of information, like ripples on a vast, hidden ocean. And if that's true, the next question is even more thrilling. Who or what is holding the projector? Black holes aren't just cosmic vacuum cleaners. They might be the universe's ultimate hard drives. Picture this: every particle, every shred of light that falls into a black hole doesn't just vanish. Instead, its information gets imprinted onto the black hole's event horizon, the point where gravity's grip becomes inescapable. This bizarre idea traces back to Jacob Bekenstein, a young physicist who in the 1970s made a startling claim: black holes have entropy. Entropy, often called the universe's measure of disorder, implies something profound. If a black hole has entropy, it must also contain information like a celestial fingerprint of everything it's ever consumed. At first, even Stephen Hawking resisted this idea. Hawking had famously shown that black holes emit radiation, slowly evaporating over eons. If they could vanish entirely, what happened to all that swallowed information? It seemed to violate quantum mechanics' golden rule: information can never be destroyed. This became known as the black hole information paradox, a puzzle so deep it threatened to unravel our understanding of reality. But the holographic principle offered a way out. Imagine the event horizon isn't just a boundary, it's a bustling surface where every bit of incoming data gets encoded, like a cosmic etch-a-sketch. Even as the black hole evaporates, that information isn't lost. It's preserved, scrambled perhaps, but never erased. Think of it like burning a book. The pages turn to ash, but if you had perfect knowledge of every molecule in that smoke and cinder, you could theoretically reconstruct the original text. In the holographic universe, the event horizon plays that role. It's not matter or energy that's stored, it's the relationships between them, the quantum threads that weave reality together. This revelation didn't just solve Hawking's paradox, it suggested something even wilder. If black holes, the densest objects in existence, can store information on their surfaces, why not the universe itself? Experiments are still catching up to these ideas, but the math holds an eerie consistency. The holographic principle transforms black holes from cosmic trash compactors into libraries, their walls lined with the stories of everything they've ever consumed. And if that's true for them, who's to say our entire universe isn't doing the same thing on a grander scale? The screen you're staring at right now, the words you're hearing, they might just be echoes from the edges of reality itself. What if the universe isn't smooth and continuous, but made of tiny, indivisible fragments like the pixels on a screen? Dive deep enough, and even space-time itself might reveal a hidden graininess, a fundamental limit to how finely reality can be divided. This is the bold claim of the pixelated universe theory, the idea that at the smallest possible scale, the Planck length, which is a millionth of a billionth of a billionth, the width of a single atom space-time, isn't a flowing fabric but a mosaic of discrete, shimmering tiles. Think of a digital photograph. From a distance, it looks seamless, vivid, alive. But zoom in far enough, and you'll see the pixels, tiny squares of color that blend together to create the illusion of depth and continuity. Now imagine applying that to the cosmos. The stars, the planets, even the empty void between them could all be built from unimaginably small space-time pixels, each carrying a snippet of information that collectively constructs our reality. This idea finds surprising support from loop quantum gravity, a radical alternative to string theory. In this framework, space isn't an empty stage but a dynamic network of interconnected loops, like an invisible spiderweb vibrating with energy. These loops can't be divided infinitely. Instead, they have a smallest possible size, a quantum of space. It's as if the universe has a resolution limit, and beyond that, the concept of smaller simply doesn't exist. But here's where things get controversial. If spacetime is pixelated, what happens to Einstein's smooth, warping geometry in general relativity? Can these two visions, quantum granularity and cosmic curvature, coexist? Some physicists argue that at everyday scales, the pixelation is so fine we'd never notice it, like how you can't see the dots in a printed newspaper unless you hold it inches from your face. Others counter that if spacetime has a built-in grain, high-energy phenomena like gamma-ray bursts might reveal subtle glitches in the cosmic code, like a video stuttering when the data rate's too high. The implications are staggering. A pixelated universe would mean that even the vacuum of space isn't truly empty. It's a seething foam of quantum fluctuations, with space-time itself flickering in and out of existence at the tiniest scales. It challenges our most intuitive notions of distance and time, suggesting that the smooth, continuous reality we experience is just an emergent illusion, a masterpiece painted with quantum dots. So is the universe really a cosmic screen, rendering existence one Planck-sized pixel at a time? The answer might lie in the faint whispers of distant cosmic explosions or the hum of particle colliders probing reality's sharpest edges. Until then, the question lingers: if you could peer deep enough into the heart of space itself, would you find endless smoothness or the shimmering static of a universe built from invisible, indivisible bits? Quantum entanglement might be the universe's secret stitching, the invisible thread holding the holographic illusion together. Picture two particles born from the same event, instantaneously connected no matter how far apart they drift. Change one and the other reacts instantly, as if space and distance between them don't exist. Einstein famously called this spooky action at a distance, but in a holographic universe, it could be the glue binding reality itself. Enter ER equals EPR, a radical idea that ties entanglement to the fabric of spacetime. Einstein and Rosen once proposed bridges wormholes linking distant points in space. Decades later, physicists Leonard Susskind and Juan Maldacena suggested something astonishing. Maybe those wormholes are entanglement. Every pair of entangled particles could be connected by a microscopic tunnel, a kind of quantum shortcut through the cosmic projection. Imagine the universe as a vast tapestry, where each thread isn't just a strand of energy but a hidden tunnel, weaving particles together in an intricate, invisible web. Here's where it gets wild. If entanglement forms these quantum bridges, then every interaction, every connection we see in the universe might arise from something deeper, a network of holographic links. Think of it like a cosmic knitting project. The three-dimensional world we experience is the finished sweater, but the real magic is in the loops of yarn, the entangled pairs that hold it all together from behind the scene. This could solve one of physics' biggest headaches: how to reconcile gravity with quantum mechanics. Gravity might not be a fundamental force at all, but a side effect of entanglement's intricate web. Picture a crowd of people holding hands in a dark room. If one person tugs, the ripple travels through the chain, unseen but undeniable. In the holographic universe, gravity could be that ripple, an emergent phenomenon from entangled particles tugging on spacetime itself. The implications are dizzying. Black holes, often seen as cosmic dead ends, might be bursting with these quantum threads, their interiors connected to distant points in space like hidden subway lines. Even the Big Bang could resemble a quantum explosion of entanglement, with every particle still tethered to its origins by invisible strings. But how do we test this? Experiments with quantum computers are hinting at these connections, simulating how entanglement might build spacetime from scratch. Meanwhile, telescopes scour the cosmos for anomalies, tiny wrinkles in reality that could betray the holographic stitching beneath. One thing's certain: if entanglement really is the universe's hidden scaffolding, then reality is far more interconnected, far more strange than we ever dreamed. And that changes everything. Juan Maldacena's anti-de Sitter space model isn't just a theory, it's a cosmic Rosetta Stone, translating between two seemingly incompatible languages of physics. On one side, you have gravity warping the fabric of spacetime in a higher dimensional realm called anti-de Sitter space, or AD-S. On the other, a quantum field theory humming along on its lower dimensional boundary, known as conformal field theory, or CFT. The revelation: these aren't separate worlds, they're mirror images, two sides of the same holographic coin. Picture a can of soup sitting on your shelf. The label wrapped around it, flat, printed with ingredients and nutrition facts, doesn't just describe the soup inside. In a profound twist, it contains the soup. Every vegetable, every spice, even the steaming broth is perfectly encoded in the two-dimensional ink on that label. That's AD-S/CFT duality in a nutshell. The soup is gravity's dance in the higher dimensional bulk of anti-de Sitter space, while the label is the quantum information dancing on its boundary. The mind-blowing implication: our three-dimensional universe, with all its stars and galaxies, might just be the label for something far stranger unfolding in a hidden dimension. Anti-de Sitter space itself is no ordinary playground. Unlike our expanding universe, AD-S curves inward like a cosmic saddle, creating a boundary where light can actually reach infinity and bounce back in finite time. It's as if the universe had walls, but instead of plaster, they're lined with quantum data. The real magic happens when you realize the gravitational events inside this warped space, colliding black holes, rippling spacetime, are perfectly mirrored by quantum interactions on its surface. A star collapsing in the bulk might appear as a flicker of entangled particles on the boundary, like shadows cast by a fire hidden behind a screen. But why does this matter for our universe? After all, we don't seem to live in anti-de Sitter space. Our cosmos is expanding, not curving inward. the answer lies in the math. Maldacena's equations revealed a universal principle: information doesn't need volume. It can live on surfaces, projecting inward to create depth, movement, even time. Think of a VR headset. The immersive worlds you explore aren't truly there, they're built from pixels on tiny screens millimeters from your eyes. The holographic universe might work the same way, with the boundaries quantum code generating the immersive illusion we call reality. Critics argue ADS is just a simplified sandbox, a toy model too neat to reflect our messy cosmos. Yet experiments with quark-gluon plasma, a super-hot state of matter created in particle colliders, show behavior eerily matching ADS/CFT predictions. It's as if nature left fingerprints pointing to a deeper connection. Even more tantalizing, black holes. Their event horizons act like natural holograms, cramming information onto surfaces while projecting gravitational drama inward. If Maldacena's duality holds, studying black holes could be like reverse engineering the universe's source code. The most radical take: time itself might be emergent in this framework. Just as a movie creates the illusion of motion from static frames, the boundaries' quantum interactions could render time in the bulk, not as a fundamental flow, but as a side effect of entanglement's intricate choreography. This flips causality on its head. What we perceive as cause and effect might just be echoes of quantum correlations playing out on the edge of everything. So is our universe a higher dimensional hologram, or is ADS/CFT just a mathematical curiosity? The debate rages, but one thing's certain: Maldacena's discovery cracked open a door to a new way of seeing reality. Whether that door leads to ultimate truth or deeper mystery, it's rewritten the rules of the cosmic game. And if the holographic principle is right, we're not just players in that game. We might be part of its projection, flickering into existence one quantum calculation at a time. One of the greatest puzzles in cosmology isn't about what's in the universe, it's about the shape of spacetime itself. After centuries of measurements, from ancient star maps to cutting-edge satellite data, the universe appears strikingly, inexplicably flat. Not flat like a sheet of paper, but in the cosmic sense, parallel beams of light stay parallel forever. Triangles drawn across galaxies add up to exactly 180 degrees, and the fabric of reality lacks any measurable curvature. This shouldn't make sense. Gravity should warp spacetime over vast distances, bending light and twisting geometry like a funhouse mirror. So why doesn't it? The holographic principle might hold the key, and it all starts with the idea that our three-dimensional reality is really a two-dimensional code enforcing cosmic flatness from the edges. Think of a soap bubble. From the outside, it's a perfect sphere curving gracefully in every direction. But if you could step inside that bubble, the surface would feel impossibly flat, no matter where you stood. That's the holographic twist. What we perceive as a flawlessly flat universe might just be an artifact of living inside a projection. If all the information encoding reality is stored on a distant, two-dimensional boundary, like the surface of that bubble, then the three-dimensional bulk we experience could inherit its flatness from that lower-dimensional blueprint. It's as if the universe's operating system has a hidden setting, rendered geometry flat by default. This dovetails eerily well with cosmic inflation, the theory that the newborn universe underwent a fantastically rapid expansion in its first fractions of a second. Inflation stretches spacetime so violently that any initial curvature gets smoothed out like blowing up a crumpled balloon until its wrinkles vanish. But here's the holographic kicker. Inflation might not be the cause of flatness, but a consequence of the universe's deeper holographic nature. If the boundary enforces flatness through its encoding, then inflation could simply be the mechanism that delivers that flatness to the projected interior. Picture a painter meticulously smoothing a canvas before applying the first stroke. The holographic boundary sets the rules, and inflation executes them. Evidence for this lurks in the cosmic microwave background, the afterglow of the Big Bang. Its temperature fluctuations are whisper quiet, just 1 part in 100,000, as if something suppressed extreme variations from the start. In a holographic framework, this could mean the boundary's quantum code has built-in error correction, limiting how wildly spacetime can curve in the projected universe. It's not perfect, those tiny fluctuations seeded galaxies, but it's strikingly close to flat, as if reality itself is running on rails laid down by a lower-dimensional architect. But could we ever test this? Surprisingly, yes. If the universe is holographic, there should be subtle signatures in how large-scale structures, galaxy clusters, cosmic voids align across vast distances. These patterns would resemble interference fringes, like the overlapping ripples from pebbles tossed into a pond. Telescopes like the Euclid space mission are already hunting for such statistical fingerprints, scanning millions of galaxies for traces of a hidden cosmic projector. Even more tantalizing, gravitational waves. If spacetime's flatness is enforced by a boundary, ripples in that fabric might carry echoes of their two-dimensional origins, like a drumhead vibrating in ways that betray its hidden anchors. The implications are staggering. A holographic solution to the flatness problem wouldn't just explain why the universe looks the way it does. It would suggest that the very laws of geometry aren't fundamental but emergent. The reason parallel lines never meet might have nothing to do with spacetime itself, and everything to do with a shadowy, lower-dimensional rulebook we're only beginning to decode. And if that's true, the next question is even more profound. What else is that boundary hiding? We take time for granted, the steady tick of seconds, the unshakable arrow pointing from past to future. But what if time isn't a fundamental part of reality? What if it's just an illusion, a side effect of something deeper at work in the holographic fabric of the universe? This isn't science fiction. Physicists like Carlo Rovelli have spent decades dismantling our intuition about time, suggesting it doesn't exist at the most basic level. Instead, what we perceive as time could be an emergent phenomenon, bubbling up from the way information is processed and projected in a holographic cosmos. Think of a flipbook. Each page holds a static image, but when you thumb through them rapidly, the illusion of motion emerges. In the holographic framework, now might work the same way, a series of quantum snapshots rendered so quickly by the universe's underlying code that we experience it as a continuous flow. Rovelli's timeless quantum gravity theory takes this further, proposing that at the Planck scale, there's no past or future, just a network of events connected by cause and effect. Time, in this view, isn't woven into the universe's blueprint. It's more like a user interface, a convenient way for complex systems like us to make sense of reality's deeper, timeless mechanics. This radical idea finds eerie support in black hole physics. When matter crosses a black hole's event horizon, from an outsider's perspective, time appears to freeze. The infalling object never quite reaches the horizon. It just smears across it like a cosmic film strip stuck on pause. But from the object's own perspective, time flows normally as it plunges inward. This paradox hints that time isn't an absolute backdrop but a relational property, emerging from interactions between systems. In a holographic universe where everything's encoded on a boundary, time might simply be the label we slap on the ever-shifting relationships between quantum bits. Even our brains could be complicit in the illusion. Neuroscientists know perception isn't instantaneous. Our minds stitch together sensory input with slight delays, constructing a seamless now from slightly outdated data. It's not unlike a video game rendering frames just fast enough to trick us into believing in a fluid world. If the brain can hack time's flow on a microscopic scale, why couldn't the universe do the same on a cosmic one? The implications are dizzying. If time is emergent, then the present isn't a universal truth, it's a local glitch, a quirk of perspective. The past and future might not be gone or unborn, but simultaneously written in the holographic boundaries data, like scenes in a script waiting to be performed. This reshapes everything from free will to entropy, suggesting the arrow of time isn't an intrinsic feature of reality, but a story we tell ourselves to navigate the projection. So the next time you check your watch, consider this. Those ticking hands might not be measuring something real. They could just be counting the universe's frames per second, a cosmic refresh rate we're wired to mistake for the flow of time itself. The Big Bang wasn't an explosion in space, it might have been an explosion of space, erupting from a hidden two-dimensional surface like a holographic firework. This radical twist on cosmology suggests that the universe's violent birth wasn't confined to a single point but unfolded as a projection, with every quark, photon, and galaxy emerging from data encoded on a cosmic boundary we can't see. If true, the aftermath of that primordial event, the cosmic microwave background, or CMB, could carry ghostly fingerprints of its holographic origins. The CMB is often called the universe's baby picture, a snapshot of the cosmos just 380,000 years after the Big Bang. It's a near-perfect sea of microwave radiation, uniform to 1 part in 100,000, but not perfectly uniform. Tiny fluctuations in temperature dot the CMB like brushstrokes on a canvas, and some of these imperfections defy expectations. Certain patterns like large-scale cold spots or oddly aligned axis of evil anisotropies don't fit neatly into standard inflation models. Could these cosmic wrinkles be artifacts of a holographic projection, glitches in the code revealing the lower dimensional surface where the universe's data was first written? Imagine blowing up a digital image until you see the pixels. The CMB might be doing something similar, stretching the universe's underlying resolution to its limits. In 2010, researchers analyzing data from the Planck satellite noticed bizarre, ring-like patterns in the CMB's polarization maps. These circles, some argued, could be echoes of pre-Big Bang events, vibrations from the holographic boundary reverberating through spacetime like ripples in a pond. Skeptics dismissed it as statistical noise, but the anomalies keep piling up. Some regions of the CMB exhibit less randomness than they should, as if the universe's randomness generator had a built-in bias, exactly what you'd expect if reality were encoded on a structured surface with finite information density. The holographic Big Bang flips the script on creation. Instead of a singularity, a point of infinite density, it proposes a transformation like a butterfly emerging from a chrysalis. The two-dimensional boundary becomes a three-dimensional universe, not by expanding into something, but by unfolding from within, like a pop-up book revealing depth where none existed before. This could explain why the universe appears so finely tuned. The constants of nature, the strength of gravity, the mass of electrons might not be arbitrary numbers but inevitable outputs of a holographic algorithm, baked into the projection from the start. Testing this won't be easy, but next-generation CMB experiments like the Simons Observatory are hunting for deeper clues. If the universe is a hologram, its quantum origins might have left subtle statistical signatures, patterns that look like cosmic barcodes when analyzed with the right math. Others are simulating holographic universes in supercomputers, watching as 2D data spontaneously generates 3D worlds. The results are eerily reminiscent of our own cosmos, with virtual galaxies clustering in ways that match telescope surveys. The most profound implication: if the Big Bang was holographic, then every atom in your body traces back to a code written on the edge of reality. You're not just in the universe, you're of it, a three-dimensional shadow cast by quantum bits dancing on a distant two-dimensional stage. And somewhere in the CMB's whisper-quiet static, the universe's original programming might still be running, waiting to be decoded. Dark energy, the mysterious force pushing the universe apart at ever-increasing speeds, has baffled scientists since its discovery in the 1990s. Conventional physics chalks it up to Einstein's cosmological constant, a static energy woven into the fabric of space itself. But what if dark energy isn't a feature of our three-dimensional world at all? What if it's a side effect of the universe's holographic skeleton, a cosmic tension emerging from the way information is packed onto its two-dimensional boundary? Picture a stretched rubber sheet. The tighter you pull it, the more energy builds in the material. Now imagine that sheet is the universe's outer edge, crammed with quantum bits encoding everything from galaxies to the thoughts in your brain. As the universe expands, that boundary stretches, but unlike rubber, it can't thin out. The holographic principle demands that information density stays constant on the surface. To maintain that equilibrium, new pixels must continuously emerge, filling the gaps as space grows. This relentless creation of information could manifest as an outward pressure, dark energy in disguise. This idea flips the script on Einstein's cosmological constant. Instead of dark energy being an arbitrary number plugged into equations to match observations, it becomes a natural consequence of the universe's holographic architecture. The math even hints at why dark energy's strength is so mind-bogglingly tiny, about 120 orders of magnitude weaker than quantum field theory predicts. In a holographic framework, that weakness isn't a fluke. It's baked into the scaling between the boundaries information and the projected volume. Critics argue this is just another way to repackage the mystery. But recent simulations of holographic universes show something striking. When you model space as emerging from a lower dimensional code, an accelerated expansion spontaneously appears, no cosmological constant required. It's as if the universe's operating system has a built-in expansion setting, activated by the way data flows between dimensions, even more compelling. The holographic approach predicts subtle deviations from the cosmological constant's behavior. Tiny wobbles in dark energies push that telescopes like Euclid and the Vera Rubin Observatory are now hunting for. The stakes couldn't be higher. If dark energy is truly holographic, it means the universe's accelerating expansion isn't driven by some invisible fluid filling space, but by the way reality renders itself at the deepest level. Every galaxy racing away from us, every future star doomed to vanish beyond the cosmic horizon, all of it could be the universe's way of balancing its books, ensuring the hologram doesn't glitch as the projection stretches into infinity. And if that's true, the boundaries code doesn't just describe dark energy, it is dark energy, whispering its presence through the relentless stretching of spacetime itself. What if the holographic universe isn't just physics, it's the operating system of a cosmic simulation? This is where Nick Bostrom's famous simulation hypothesis collides head-on with the holographic principle, merging philosophy with cutting-edge science. Bostrom's argument is simple yet staggering. If advanced civilizations ever develop the power to run ancestor simulations, hyper-realistic recreations of their past, then the odds are overwhelming that we're inside one. Now layer that with the holographic idea. If reality is a projection from a two-dimensional boundary, could that boundary be the hardware running the simulation, with our lives just lines of code etched onto its surface? Think of it like this. In a video game, every mountain, every NPC, even the weather is rendered from mathematical instructions stored in memory. But the game world isn't inside the computer's circuits, it's a projection, an interactive hallucination conjured by the GPU. The holographic universe could work the same way. The boundary isn't just storing information, it's processing it, executing the rules that make galaxies spin, electrons buzz, and your coffee cup feel solid in your hand. Suddenly, the simulation argument isn't just about whether we're real, it's about what kind of reality we're inhabiting. A holographic simulation wouldn't be pixels on a screen. It'd be spacetime itself rendered from quantum bits, with every law of physics a deliberate subroutine. This raises existential questions that rattle the foundation of identity. If you're made of projected information, are you still you, or just an avatar in someone else's cosmic game? Some philosophers argue it doesn't matter, consciousness is consciousness, whether running on neurons or quantum fields. Others counter that a simulated self is no more real than a character in a novel, no matter how vivid the illusion. The holographic twist adds a new layer. Even if we're just data, that data might be fundamentally real in its own right. After all, in a universe where information is the bedrock of existence, isn't everything, even the simulators, just another pattern in the code? Here's where physics throws a lifeline. Unlike pure speculation, the holographic principle offers testable clues. If spacetime is pixelated at the Planck scale, future quantum gravity experiments might detect its granularity, like feeling the grit of sandpaper beneath the universe's smooth facade. Strange quantum behaviors, like particles existing in multiple states until observed, could be processing lags in the cosmic rendering engine. Even dark energy might be a memory management issue, the simulation struggling to allocate resources as the universe expands. But the most haunting implication isn't about technology, it's about intention. Why would someone run such a simulation? Are we someone's ancestor simulation, a historical reenactment, an art project, a cosmic experiment testing the limits of complexity? Or worse, could we be the abandoned byproduct of a long-dead civilization, left running in the void like a forgotten server in a basement? The holographic principle doesn't answer these questions, but it gives them a terrifyingly plausible framework. So where does that leave us, staring into the abyss between two worldviews? 1. We're fleeting patterns in an alien simulation, our suffering and joy as meaningless as a screensaver's swirls. 2. We're participants in a universe so profoundly interconnected that the distinction between simulated and real melts away. In a holographic cosmos, the code is the cosmos. And if that's true, the real question isn't whether we're in a simulation, it's whether the universe has ever been anything else. Consciousness might not be locked inside your skull. It could be a holographic phenomenon, stitching together reality from fragments of quantum information scattered across the fabric of spacetime. This audacious idea traces back to neuroscientist Carl Pribram, who in the 1970s noticed something odd about memory. No matter how much brain tissue you remove, memories don't vanish the way you'd expect if they were stored in specific locations. Instead, they degrade gracefully, like a photograph slowly fading. Pribram realized this eerily resembled holograms, where every fragment of the film contains the whole image, just at lower resolution. His holonomic brain theory proposed that your mind doesn't process information like a hard drive. It interferes with it, like ripples overlapping in a pond, creating the rich tapestry of perception from waves of quantum vibrations. Dive deeper and the implications become staggering. If the brain encodes experience holographically, then consciousness itself might not be generated solely by neurons firing. It could emerge from quantum coherence, tiny particles in your synapses behaving like entangled actors in a cosmic play, instantly influencing each other across microscopic distances. This aligns with controversial quantum mind theories, which suggest that microtubules, tiny protein structures inside neurons, might harness quantum effects to orchestrate thought. Critics dismiss this as biological fantasy. Quantum states are notoriously fragile, easily shattered by the warm, wet chaos of the brain. But if the universe is fundamentally holographic, those quantum whispers might persist longer than we think, shielded by the same principles that let black holes preserve information on their surfaces. Here's where it gets speculative and thrilling. Philosopher David Chalmers once argued that consciousness could be a fundamental property of the universe, like mass or charge. In a holographic framework, that property might not reside in matter but arise from the way information is woven together at the quantum level. Picture a symphony where no single instrument holds the melody. The music exists in the relationships between notes. Your sense of self, your thoughts, your awareness of these words right now, could be the universe's way of playing the data encoded on its boundary, translating quantum correlations into the illusion of a continuous inner world. The skeptics aren't wrong to raise eyebrows. No one's found microtubules performing quantum computations in living brains, and holonomic theory remains on the fringes. But consider this, if the holographic principle holds, then the boundary between mind and universe blurs. Your brain might not create consciousness so much as tune into it, like a radio plucking symphonies from static. Near-death experiences, collective intuition, even déjà vu phenomena science struggles to explain, could be glitches in the projection, moments when the hologram's underlying code flickers into view. Whether Pribram's theory withstands time or collapses under scrutiny, it forces a profound question. If reality is a hologram, is consciousness the image or the light that brings it to life? The answer might not lie in our biology, but in the quantum threads stitching the cosmos together. And that changes not just how we see the brain, but how we see ourselves in the grand cosmic theater. Fractals aren't just mesmerizing mathematical art, they might be the universe's hidden blueprint, repeating the same intricate patterns from the smallest quantum flutter to the vastest cosmic web. This is the essence of fractal holography, a theory that takes the holographic principle and twists it into something even stranger. What if the universe's information isn't just encoded on a distant boundary, but woven into an endless cascade of self-similar scales, like a hall of mirrors where every reflection holds another universe inside it? Think of a fern. Zoom in on one leaflet and you'll find it's made of smaller leaflets, each echoing the whole. Zoom in further and the pattern repeats again, a perfect recursion of shape and structure. Now imagine that same principle applied to spacetime itself. At the Planck scale, where space is thought to be pixelated, those pixels might not be uniform blocks. They could be tiny holograms, each containing a scaled-down version of the larger universe's information, like Russian nesting dolls where every layer whispers the same cosmic story. This isn't pure speculation. When physicists analyze the quantum entanglement of space-time, how particles remain mysteriously linked across distances, they find entanglement entropy follows scaling laws eerily reminiscent of fractal geometry. It's as if the universe's quantum code is designed to repeat with every region of space, no matter how small, mirroring the relational patterns of the whole. Even black holes hint at this. The way information spreads across their event horizons resembles the branching, self-similar structures of fractal coastlines, endless complexity emerging from simple recursive rules. The implications are mind-bending. If the universe is a fractal hologram, then the boundary encoding reality might not be a single, distant surface. It could be everywhere, nested within every atom, every photon, every fleeting fluctuation of the quantum vacuum. Time itself might unfold in fractal rhythms, with moments echoing across scales like the beats of a cosmic drum. And consciousness, if the brain's neural networks exhibit fractal activity, as some neuroscientists suggest, then our minds might be tuning into this holographic recursion, perceiving reality through layers of self-similar information. Could we ever test this? Some researchers are looking for fractal signatures in the cosmic microwave background, hunting for patterns that repeat across angular scales. Others simulate holographic universes with fractal dimensions, watching as virtual galaxies arrange themselves in eerily familiar spirals, the wildest possibility. If fractal holography is real, then every particle in your body carries a whisper of the whole cosmos, not just as data, but as a living, breathing fragment of infinity. The universe wouldn't just contain multitudes, it would be multitudes folding inward and outward forever, a holographic echo without end. The Higgs field is often described as a cosmic molasses, an invisible syrup pervading all of space, slowing down particles as they trudge through it, giving them the illusion of mass. But what if this molasses isn't filling space like liquid in a jar? What if it's more like the shimmer on the surface of a pond, a two-dimensional effect that only appears three-dimensional when we interact with it? This is the radical possibility at the heart of holographic Higgs theory. The mechanism behind mass might not live inside the universe but on its boundary, written into the fabric of reality like a watermark on cosmic parchment. Picture a crowded concert. The crowd's energy makes it hard to move. You're jostled, slowed, as if wading through thick mud. Normally, we'd say the crowd occupies the space, creating resistance. But holography flips this. The resistance, the Higgs effect, might not come from something inside space, but from data on the boundary, like security gates at the venue's edges controlling the flow. The field we call Higgs could be a projection, an emergent phenomenon arising from quantum interactions on the universe's outer shell. The math hints at this. In Maldacena's AD/S/CFT correspondence, properties like mass and charge in the higher dimensional bulk universe correspond to specific quantum states on the lower dimensional boundary. Just as a 3D hologram emerges from 2D interference patterns, mass might emerge from entangled quantum bits on the edge of spacetime. Imagine the boundary as a vast mosaic where each tile represents a quantum state. The way these tiles are arranged, their collective hum determines how particles feel mass in the projected universe, like an orchestra tuning their instruments to create the illusion of weight. This reshapes our understanding of the Higgs boson, the celebrated particle discovered at CERN in 2012. If the field is holographic, the boson might not be a fundamental building block but a kind of echo, a ripple in the projected molasses caused by disturbances in the boundary's code. It's the difference between finding a fish in the ocean and realizing the fish was just a reflection dancing on the water's surface all along. Critics argue this complicates an already mysterious mechanism. But the holographic view could solve lingering puzzles like why the Higgs mass is so unnaturally light compared to quantum predictions. If mass is dynamically computed on the boundary, the numbers might balance differently, avoiding the need for contrived fine-tuning in the equations. Future particle colliders could hunt for anomalies, subtle deviations in how Higgs bosons interact that betray their holographic origins, like glitches in a simulation revealing its underlying resolution. The most poetic implication: if the Higgs field is holographic, then the very solidity of your body, the weight of your hands, the resistance of your bones traces back to a shimmering code on the edge of existence. You don't just have mass, you're reading it moment by moment from the universe's deepest layer of programming. Wormholes have long been the stuff of science fiction cosmic shortcuts, bending space and time to connect distant points in an instant. But what if these fantastical tunnels aren't just theoretical curiosities? What if they're the universe's built-in wiring, stitching together reality through the holographic principle? The ER=EPR conjecture takes this idea and runs with it, proposing that every pair of entangled particles, those spookily linked quantum twins, might be joined by a microscopic wormhole, a hidden tunnel through the fabric of spacetime. Picture two dice tumbling in separate galaxies. Under normal circumstances, rolling one shouldn't affect the other. But if they're entangled, changing the state of one instantly alters its partner, as if some invisible thread connects them across the void. Einstein called this spooky action at a distance. The holographic twist, that thread might literally be a wormhole, not a tunnel through space, but a flaw in space, a tear where the universe's two-dimensional code folds back on itself like a glitch in the matrix. This flips how we imagine interstellar travel. Forget rockets lumbering across light years. If ER=EPR holds, crossing the cosmos might mean navigating a labyrinth of entanglement, hopping from one quantum connection to another like stepping stones through a holographic river. Christopher Nolan's Interstellar gave us a visceral taste of this with its portrayal of Gargantua's wormhole, a shimmering sphere warping space like a funhouse mirror. But the holographic version is stranger. These wormholes wouldn't be celestial subway tunnels, they'd be relationships, living threads woven into the quantum fabric, tying the universe together from the inside out. The catch, scaling this up, isn't as simple as finding a bigger wormhole. Entanglement is delicate, shattered by the slightest disturbance. To traverse a holographic shortcut, you'd need to preserve quantum coherence across macroscopic distances, a feat even advanced civilizations might struggle with. But here's the tantalizing part. Black holes could be nature's proof of concept. Their interiors might be threaded with wormholes leading to other regions of space-time, or even other universes like cosmic backdoors hidden in plain sight. The implications ripple beyond travel. If wormholes bind entangled particles, then the universe isn't just expanding, it's networking, growing a web of holographic connections where every interaction leaves a thread. Time dilation, quantum jumps, even the apparent randomness of particle behavior could all be side effects of this hidden infrastructure. The universe isn't just a place. It's a conversation with wormholes as the whispering tunnels between syllables. So next time you hear about entangled particles, don't just think of them as distant pen pals. They might be neighbors, separated only by a fold in the cosmic origami, a holographic handshake waiting to be decoded. For over a century, physics has been torn between two rival visions of reality. On one side, quantum mechanics rules the microscopic realm, where particles pop in and out of existence and reality remains fuzzy until observed. On the other, Einstein's general relativity paints spacetime as a smooth, curving stage where massive objects bend the fabric of the cosmos. These frameworks work flawlessly in their own domains, yet whenever they meet, the math explodes into nonsense. Black holes should be infinitely dense points. The Big Bang singularity defies logic. Something fundamental is missing: a theory of quantum gravity to unite these warring perspectives. String theory once seemed the prime candidate, weaving reality from vibrating one-dimensional threads. But after decades, it remains untestable, a beautiful mathematical castle floating in the abstract. The holographic principle offers something radically different, not just a theory, but a revelation that the conflict itself might be an illusion. Think of holography as cosmic diplomacy. Instead of forcing quantum mechanics and relativity to reconcile in our three-dimensional world, it suggests they're already unified just on a two-dimensional boundary we can't see. Picture two diplomats arguing in a hall of mirrors. They're not actually disagreeing, they're just seeing reflections of the same truth from different angles. In Maldacena's AD/CFT correspondence, the equations of quantum field theory on the boundary perfectly mirror those of gravity in the bulk. No forced mergers, no extra dimensions, just an elegant duality where both theories emerge as different expressions of the same underlying reality. This approach sidesteps string theory's biggest hurdle, testability. While strings are vanishingly small, far beyond any foreseeable microscope, holography leaves fingerprints we might actually detect. Take quark-gluon plasma, the primordial soup created in particle colliders. Its behavior matches holographic predictions with uncanny precision, as if we're glimpsing the boundary's quantum code casting shadows in our world. Even black holes, those notorious destroyers of information, become laboratories. If the holographic principle holds, their event horizons should exhibit specific patterns in how they scramble data, like cosmic encryption we could crack with gravitational wave telescopes. Critics argue holography hasn't yet delivered a full quantum gravity theory, but its power lies in its economy. Where string theory requires 10 dimensions and supersymmetry, holography needs just the familiar 3 or 4, counting time, projecting them from a two-dimensional surface using known physics. It's the difference between building a ladder to reach an apple and realizing the apple was a painting on the wall all along, no ladder needed. The most tantalizing clue. Entanglement entropy. In quantum mechanics, entangled particles share mysterious correlations. In general relativity, black holes have entropy proportional to their surface area. Holography links these through a single elegant equation. The entanglement between boundary regions is the space-time geometry in the bulk. It's as if the universe whispered its operating manual: gravity isn't a force, but the cosmic manifestation of quantum connectedness. So while string theorists chase shadows in higher dimensions, holography offers a map to the universe's source code, written not in hidden strings, but in the quantum threads already woven through reality. The bridge between quantum and relativistic worlds might not lie ahead. It could be beneath our feet, in the holographic surface we've yet to fully read. And with every black hole echo, every quark gluon flicker, we're decoding another line. If our universe is a hologram, then why stop at just one? The holographic principle might not confine itself to a solitary cosmic projection. Instead, it could open the door to infinite others, each a unique page in a vast multidimensional codex. This is the holographic multiverse, where every universe is a self-contained projection from its own lower dimensional boundary, like separate films playing simultaneously on the same celestial projector. But unlike traditional multiverse theories, where alternate realities branch randomly or exist in disconnected bubbles, the holographic version suggests these universes could be intricately linked, their boundaries interleaved like sheets in a cosmic ream of paper, resonating with shared quantum data. Now imagine a library where every book is written in a language that describes not just stories but entire realities. The holographic multiverse operates similarly. Each universe's boundary encodes its physical laws, constants, and even the flow of time, all etched into the fabric of its two-dimensional surface. Some pages might depict universes where gravity is stronger, light travels slower, or life never emerged. Others could be nearly identical to ours, differing only in the spin of a single electron at the dawn of time. The key difference in this framework, the multiverse isn't just a collection of disconnected worlds. It's a network with information potentially leaking between boundaries, creating subtle echoes or symmetries across realities. This idea converges strikingly with brane cosmology, a cornerstone of string theory. In that model, our universe might be a three-dimensional brane, floating in a higher dimensional space, occasionally colliding with others to trigger big bangs. But the holographic twist flips the script. Instead of branes bumping in some unseen bulk, each universe could be a projection from its own boundary, with no higher dimensional space needed. The connections between them wouldn't rely on physical proximity, but on entangled quantum data, like two computers sharing a wireless signal despite being miles apart. Max Tegmark's mathematical universe hypothesis takes this even further. He proposes that every mathematically possible structure is a physical reality, meaning universes with entirely different laws aren't just probable but inevitable. Combine this with holography, and suddenly, those mathematical structures aren't abstract equations. They're algorithms running on the cosmic projector, each generating a universe from the precise arrangement of quantum bits on its boundary. A universe where pi equals 4, a reality with 19 dimensions. In a holographic multiverse, these aren't fantasies. They're just alternative renderings, different programs executing in the same cosmic quantum computer. The implications are staggering. If holographic boundaries can communicate through quantum entanglement, wormholes, or some deeper mechanism, then the walls between universes might be more porous than we think. Cosmic anomalies like the mysterious cold spot in our universe's background radiation could be bruises from a collision with another boundary's data. Even dark energy might not be unique to our universe. It could be a shared feature of the holographic network, a kind of system-wide setting ensuring projections don't glitch as they expand. The biggest question: if the multiverse is holographic, does that mean all boundaries are ultimately part of a single, transcendent code? Are we just one paragraph in an infinite cosmic story, or is there a deeper unity weaving every universe together? The answer might lie in the quantum whispers between event horizons, or in the faint, statistical fingerprints hiding in the static of space itself. Until then, the holographic multiverse remains the most tantalizing frontier, one where every universe is a projection, every reality a shadow, and every boundary a door waiting to be opened. Imagine stuffing the entire Library of Congress into a sugar cube, not just the books, but every word, every ink molecule, even the whispers of readers long gone. That's the staggering density implied by Jacob Bekenstein's bound, a fundamental limit dictating how much information any region of space can possibly hold. In the 1970s, this unassuming physicist made a discovery that would ripple through cosmology. The maximum entropy, or information contained within a volume, isn't proportional to its size, but to the area of its surface. It's as if the universe has a cosmic filing system where data isn't stored in the room itself, but on the walls enclosing it. This bizarre rule gels perfectly with the holographic principle. If reality is a projection from a two-dimensional boundary, then Bekenstein's bound isn't a limitation, it's a feature. The universe isn't losing information by compressing it onto surfaces. It's optimizing it like a master engineer distilling an entire symphony into a flawless vinyl groove. Think of a black hole again. Crush a star into oblivion, and according to Bekenstein, every bit of information about that star gets encoded on the event horizon's surface at a rate of 1 bit per 4 Planck areas. That's nature's ultimate data compression, and it suggests something profound. The cosmos might be running on a cosmic zip file, where the illusion of three-dimensional fullness emerges from two-dimensional efficiency. But how does this apply beyond black holes? Take your smartphone. Its memory chips store data in 3 dimensions with bits stacked in layers. Yet Bekenstein's bound implies that at fundamental scales, this volumetric approach hits a wall. There's a hard ceiling to how much information you can cram into any space, and that ceiling is set by surface area, not volume. It's why futurists speculate about ultimate physical limits to computing. Even if we could manipulate every atom in a processor, the universe itself would eventually say, no more. The holographic principle offers a way out. If information is fundamentally surface-bound, future tech might ditch 3D storage altogether, embracing the same 2D encoding the cosmos uses. This raises a tantalizing question. Is the universe lazy? Physicists love efficiency, and nature seems to adore it even more. From the elegant parsimony of Einstein's equations to the minimal energy states of quantum particles, reality often chooses the path of least resistance. Holography fits right in. By storing information on boundaries rather than stuffing it into volumes, the universe might be conserving the ultimate resource itself. Every cubic light-year of empty space wouldn't need its own independent data. It's all handled at the edges, like a cosmic cloud computing network where the periphery does the heavy lifting. The implications ripple into philosophy. If Bekenstein's bound holds, then the richness of your conscious experience, every memory, sensation, and thought, might not be stored in your brain's volume, but somehow on its metaphorical surface. It's a wild idea, but not outlandish in a holographic framework. Even more unsettling, if information is fundamentally limited, could there be regions of the universe where reality starts to pixelate, where the cosmic hard drive runs out of sectors and the simulation, if that's what this shows it seems? For now, Bekenstein's bound remains a theoretical beacon, guiding us toward a deeper truth about the universe's architecture. It whispers that the cosmos isn't just stranger than we imagine. It might be leaner, more optimized, and more holographic than we ever dreamed. And if that's true, then every star, every atom, every fleeting thought is riding on the thinnest possible layer of reality, a shimmering surface where all the information lives and all the magic begins. Quantum mechanics has always had an uncomfortable secret. Reality seems to change when we look at it. Particles exist in blurry superpositions until measured, then snap into definite states as if embarrassed to be caught. This observer effect has baffled scientists for decades, But in a holographic universe, this quantum quirk takes on a spine-tingling new meaning. What if measurement isn't just observing reality, but updating it? Picture a video game where distant landscapes only render when you turn to face them. The holographic universe might work similarly, with one crucial difference. Instead of graphics cards doing the rendering, conscious observation could be the trigger that updates the boundary's quantum code, projecting definite reality from potentiality. Every time you measure an electron's position, you're not just seeing where it is, you're compelling the cosmic hard drive to rewrite that pixel in the projection. This turns Schrödinger's famous cat thought experiment on its head. The cat isn't both dead and alive until we peek inside the box. The very act of peeking instructs the holographic boundary to choose a state, locking in one version of events across the entire simulated theater. This idea electrifies an old debate: does consciousness create reality? Traditional physics brushes this aside. Observation just means interaction with any measuring device. But holography reintroduces the specter of sentience. If reality emerges from information processing, could conscious observers be privileged nodes in that network? Some interpretations suggest yes. The boundary doesn't update indiscriminately. It requires irreversible quantum Darwinism, information becoming amplified and stable enough to enter the shared holographic record. Your brain, constantly collapsing quantum uncertainties into classical perceptions, might be doing more than interpreting reality. It could be curating it. Yet the holographic view tempers this solipsism. You're not rendering reality alone. You're part of a collective consensus engine. Think of Wikipedia. No single edit defines an article, but the accumulation of changes creates a stable, agreed-upon version. Similarly, every observation across the cosmos, from photons hitting retinal cells to particle detectors clicking in labs, could be collaborative edits to the universal wiki, with the boundary integrating all inputs into a consistent projection. This explains why we all share the same basic reality despite quantum uncertainties lurking beneath. The spookiest implication, time's arrow, might emerge from this process. Quantum possibilities exist timelessly until observation collapses them into sequences. In holographic terms, the present moment could be the universe's refresh rate, the interval between boundary updates where quantum potentials resolve into classical nows. Your perception of time flowing might just be the cosmic server processing trillions of observer-induced calculations per second. Could we test this? Delayed choice experiments already play with quantum retrocausality, where present choices seem to alter past events. In a holographic framework, these might not be paradoxes but glitches revealing the boundaries, rendering latency. Future quantum internet networks with entangled nodes spanning continents could probe whether conscious observation locally affects remote systems faster than light, a smoking gun for holographic updating. The takeaway isn't that we're gods conjuring worlds with our gaze. Rather, we're active participants in a universe that only crystallizes when observed, not because we're special, but because observation is the universe's way of reading its own source code aloud. Every look, every measurement, every thought might be a whispered command to the cosmic projector. Render this next frame. Dark matter has always been the universe's quiet ghost, felt but never seen, its gravitational fingerprints bending galaxies and sculpting the cosmos while eluding every detector we've built. For decades, physicists have chased candidates like WIMP, weakly interacting massive particles, or actions, hypothetical ultralight particles drifting like cosmic mist. But what if we've been searching in the wrong dimension? Enter holographic dark matter, the tantalizing idea that this invisible scaffolding isn't made of particles at all, but is instead a shadow play, a three-dimensional echo of quantum interactions unfolding on the universe's two-dimensional boundary. Think of it like a puppeteer's hands casting silhouettes on a wall. The puppets, our galaxies, move as if guided by unseen forces, but the real action isn't happening on the stage. It's coming from the puppeteer's fingers moving behind the scenes. In the holographic framework, dark matter's gravitational tug could arise from quantum data processing on the boundary, projecting forces into the bulk universe that mimic the presence of invisible mass. This wouldn't just explain dark matter's refusal to interact with light. It would redefine what dark matter is. Instead of a sea of exotic particles, it's a gravitational artifact, a side effect of the universe's source code executing its grand projection. Compare this to traditional candidates. WIMP, for all their theoretical elegance, remain stubbornly absent in underground detectors, their predicted collisions with ordinary matter never materializing. Actions, though lighter, still rely on speculative quantum fields waiting for validation. Holographic dark matter sidesteps these hurdles entirely. No new particles needed, just a reinterpretation of how gravity emerges from the boundary's quantum entanglement. It's the difference between hunting for invisible ink on a page and realizing the words were never on the page to begin with, but encoded in the printer's software. The math behind this is as breathtaking as it is counterintuitive. In Maldacena's add S/CFT duality, certain configurations of quantum fields on the boundary correspond to gravitational effects in the bulk, including phenomena that look like dark matter. Picture a cosmic glitch where the projection doesn't perfectly align, leaving gravitational smudges that skew galactic rotations and warp galaxy clusters. These smudges wouldn't interact electromagnetically because they're not things, they're imperfections in the rendering, like a video game's physics engine miscalculating the weight of an object. This could solve one of dark matter's longest-standing puzzles, the missing satellites problem. Computer simulations predict thousands of dwarf galaxies orbiting Milky Way-like systems, yet we observe far fewer. If dark matter is holographic, its distribution might not follow the clumpy rules of particle-based models. Instead, boundary dynamics could naturally suppress small-scale structure, smoothing out the excess dwarfs like a cosmic algorithm optimizing its output. Critics argue this trades one mystery for another. How exactly does boundary data translate to gravitational anomalies? But here's the beauty. Holography doesn't just explain dark matter, it predicts subtle deviations from particle-based models. Certain galactic rotation curves, for instance, show quirks that WIMP struggle with but holography might naturally accommodate, like tighter correlations between visible matter and gravitational effects than expected. Upcoming telescopes like the Vera Rubin Observatory could spot these telltale signs, hunting for galactic structures that bend the rules just enough to betray their holographic origins. The wildest implication: if dark matter is truly a boundary effect, then our search for it has been like fish in a pond hunting for the source of ripples, never realizing the disturbance came from someone tapping the water's edge. The real answer might not lie in some undiscovered particle, but in the invisible hand that writes the universe's laws onto the fabric of reality itself. And if that's true, the key to unlocking dark matter's secrets won't be found in a detector buried underground. It's written in the quantum language of the cosmos, waiting to be decoded from the edge of everything. If reality is a hologram, then like any digital projection, it must have a resolution, a smallest possible pixel, beyond which you can't zoom further. Enter the Planck area, a mind-bendingly tiny measurement of about 10 to the minus 70 square meters, named after physicist Max Planck. To grasp this scale, imagine shrinking a single atom down to the size of our solar system. The Planck area would still be smaller than a hydrogen atom in that shrunken universe. This unimaginable dimension isn't just theoretical minutiae, it's the proposed fundamental unit of spacetime's fabric, the indivisible tile in the cosmic mosaic. The math behind this is profound. Quantum mechanics tells us that at the smallest scales, everything becomes grainy. Energy comes in packets, light in photons. Extending this to spacetime itself, the Planck area emerges as the smallest meaningful measurement of space, derived from three universal constants: gravity, quantum behavior, and light speed. It's nature's way of saying, beyond this point, the concept of size breaks down. This granularity hints at something extraordinary. That smooth, continuous spacetime might be an illusion, like the fluid motion of a movie hiding its 24 frames per second. Scientists at Fermilab's Holometer project took this idea literally. Their machine, the most sensitive laser interferometer ever built, was designed to hunt for spacetime's hypothesized fuzziness. Picture two laser beams traveling down perpendicular paths, bouncing back to combine into a steady interference pattern. If spacetime is perfectly smooth at all scales, that pattern stays rock solid. But if Planck scale pixels exist, quantum fluctuations should make spacetime jitter ever so slightly, like static on an old TV screen, the holometer's goal. Detect that jitter, catching reality's pixels in the act of flickering. The results were tantalizing but inconclusive. While the holometer found something, a faint, unexpected noise at exactly the right scale to suggest holographic fuzz, it couldn't definitively rule out more mundane sources of interference. Think of listening for a whisper in a thunderstorm. The signal might be there, but the noise makes it impossible to be sure. Still, the experiment proved something revolutionary. We can try to measure reality's resolution. Future upgrades or more sensitive detectors might yet spot the telltale pixelation, turning the holographic principle from abstract math into observable fact. What makes this quest so electrifying is what it implies about existence itself. If spacetime has a pixel size, then at the deepest level, the universe operates like a cosmic computer screen, rendering reality by updating these Planck-scale tiles trillions of times per second. Your body, the stars, even the vacuum of space, all would be dynamic patterns flashing across this fundamental grid. The holometer's hunt for fuzz isn't just about physics, it's about probing the very nature of reality's code. And if that code exists, the next question is unavoidable. Who or what is running the program? Quantum fields are the invisible stagehands of the universe. Every electron that zips through a wire, every photon that lands on your retina, even the Higgs boson granting mass to particles, all emerge from these vibrating, omnipresent entities. But what if these fields aren't filling space like an infinite, invisible mist? What if they're holographic projections, their complex dances choreographed from data etched onto the universe's two-dimensional boundary? This is the spine-tingling premise of holographic quantum field theory, where the building blocks of reality aren't just described by equations, they're rendered in real time by a cosmic quantum computer. Take the electron field. In standard physics, it's an invisible tapestry stretching through all of space, its excitations manifesting as the electrons we know. But holography flips this view. Instead of a field permeating three dimensions, the electron's properties, its mass, charge, spin, could be encoded on the boundary as entangled quantum bits, updating dynamically like pixels on a screen. When you detect an electron, you're not interacting with a discrete particle, you're triggering a boundary update, compelling the projection to resolve that point in the hologram. It's the difference between touching a shadow and realizing the shadow is being cast by someone moving a flashlight behind a curtain. Feynman diagrams, those iconic squiggles physicists used to map particle interactions, take on a new life in this framework. Normally, they're just bookkeeping tools, a shorthand for calculating probabilities. But holographically, they could be literal stickers on the boundary, each diagram representing a quantum transaction etched onto the edge of reality. A particle collision in a lab, that's the projection of two Feynman stickers merging and recomputing on the cosmic hard drive. Even the infamous virtual particles popping in and out of existence in quantum foam might just be glitches in the rendering, artifacts of the boundaries code processing probabilities before resolving them into observable events. This reshapes how we see forces like electromagnetism. Normally, photons are ripples in the electromagnetic field propagating through space. Holographically, those ripples could be surface-level updates, like a pebble dropped into a pond where the pond's edge is the boundary, and the ripples are computations fanning outward. The photon you see is the result of that computation, not the computation itself. This aligns eerily with quantum weirdness. The double-slit experiment's wave-particle duality might not be a particle choosing how to behave, but the projection switching rendering modes based on the observer's measurement settings. The implications cascade into particle physics' deepest puzzles. Why do quantum fields have the exact properties they do? Holography suggests these aren't arbitrary constants but emergent features of boundary dynamics, like the resolution and color depth of a screen shaping the images it displays. Even the Higgs mechanism, the process granting particles mass, could be a shadow play. The boundary's quantum entanglement patterns might simulate resistance, creating the illusion of mass in the projected universe. It's as if the cosmic code has a subroutine labeled "make things heavy," and every particle's weight is just its assigned value in the algorithm. Critics argue this trades tangible fields for abstract computations. But recent simulations of holographic quantum systems show tantalizing matches to real-world particle behavior, as if the universe's source code leaves fingerprints in the math. At CERN, researchers are probing whether high-energy collisions produce entanglement patterns predicted by holographic models, like finding a programmer's signature hidden in a video game's graphics. If confirmed, it would mean the Large Hadron Collider isn't just smashing particles, it's stress-testing the universe's rendering engine, the most poetic twist. In this view, the quantum fields underpinning reality aren't things at all. They're the universe's way of streaming itself into existence, frame by frame, from a boundary we'll likely never see. Every electron, every quark, every force you've ever felt might just be a holographic echo, a whisper from the edge of everything, reminding us that the deepest layer of reality isn't a place but a process. The second law of thermodynamics has long been physics' unshakable rulebook. Entropy always increases, disorder marches forward, and chaos inevitably grows. But what if this law isn't about the universe's volume at all? What if it's really a cosmic memo from the edge of reality, a ledger keeping track of information on the holographic boundary? This radical rewrite begins with black holes, those infamous destroyers that somehow became the key to unlocking entropy's deepest secrets. When Jacob Bekenstein first proposed that black holes have entropy, it sent shockwaves through physics. Entropy implies information, and information was supposed to vanish forever in a black hole's maw. But Bekenstein's math was undeniable. A black hole's entropy isn't proportional to its volume, but to the area of its event horizon. Imagine a cosmic hard drive where data isn't stored inside the device, but etched onto its outer shell. That's the holographic twist. The second law isn't counting disorder in 3 dimensions. It's tallying pixels on a 2-dimensional screen at the universe's edge. Hawking radiation turned this idea into fireworks. When black holes slowly evaporate, they don't just vanish. They leak particles carrying entropy back into the universe. Here's the kicker: the information encoded on the horizon isn't lost. It's radiated away, scrambled but preserved, like a document shredded then perfectly reassembled. This wasn't just a black hole quirk. It hinted that all entropy might be holographic, with the second law acting as a cosmic accountant tracking information flow between the boundary and our projected reality. Picture a boiling pot of water. Normally, we'd say entropy increases as heat spreads and bubbles churn. But holographically, that chaos is just surface-level turbulence. The real action is on the pot's rim, where quantum bits update to reflect the simmering disorder inside. Even more mind-bending, this could solve the infamous arrow of time problem. Why does entropy only grow forward? Because the boundary's quantum computations are irreversible, like a computer that can't run its code backward without crashing. Time's flow might just be the universe's way of preventing cosmic blue screens. The implications rewrite thermodynamics textbooks. Heat death, the universe's predicted cold, uniform end, might not be about maximum disorder in 3D space, but about the boundary reaching equilibrium, its quantum bits settling into a static pattern. Even life's complexity fits here. Organisms temporarily defy entropy by exporting disorder, eating, excreting, shedding heat. Holographically, life could be a local eddy in the boundary's data stream, a fleeting fluctuation in the cosmic code resisting the inevitable flush. So next time you spill coffee and mourn the irreversible mess, remember, you're not just watching entropy win, you're glimpsing the universe's projection flicker, one boundary update at a time. The universe seems suspiciously fine-tuned for life. Adjust gravity by a hair, tweak the strength of electromagnetism just slightly, and stars wouldn't form, molecules wouldn't bond, and life as we know it would be impossible. Coincidence? Or is there something deeper at play? Enter the holographic anthropic principle, a mind-bending twist on the classic fine-tuning problem that asks, what if life exists because the holographic universe's coding language permits it? Picture a video game where the rules gravity, friction, collision physics aren't arbitrary, but carefully calibrated to allow players to jump, climb, and interact. Now scale that up to cosmic proportions. In a holographic framework, the constants of nature might not be random numbers. They could be system requirements, the minimum specifications needed for the universe's projection to sustain self-referential complexity, including conscious observers like us. This isn't just philosophical hand-waving. The holographic principle's mathematical backbone suggests that certain boundary conditions naturally favor entangled, information-rich structures, precisely the kind that give rise to galaxies, planets, and ultimately, life. Lee Smolin's cosmological natural selection offers a provocative parallel. He proposed that universes could reproduce inside black holes, with each new cosmos inheriting slightly tweaked physical constants. Over cosmic generations, universes that produce more black holes, and thus more offspring, dominate the multiverse. The holographic version flips this. Instead of selection favoring black hole production, it might favor boundary configurations that maximize information processing. Life, in this view, isn't an accident, it's the universe's way of reading its own source code. Critics argue this skirts dangerously close to intelligent design. But the holographic anthropic principle doesn't invoke a programmer, just a statistical inevitability. In an infinite or near-inverse multiverse of holographic projections, only universes with bio-friendly rules will ever be observed because the others lack observers entirely. It's like asking why you're holding a winning lottery ticket. The losing ones don't get held up and examined. The eerie beauty, this could explain why quantum mechanics, with its observer-dependent realities, plays such a central role in physics. In a holographic universe, observation isn't passive. It's participatory, a feedback loop between the boundaries code and the structures it renders. Life isn't just permitted by the rules, it's woven into them, a necessary feature of a self-aware cosmos. So next time you marvel at the universe's perfection, remember, you're not just a passenger in reality. You might be its ultimate validation, the proof that the hologram knows it's being watched. Time crystals sound like something ripped from a sci-fi novel, structures that repeat not in space, but in time, ticking away without energy input like cosmic perpetual motion machines. First proposed by Nobel laureate Frank Wilczek in 2012, these bizarre quantum phases of matter defy one of nature's most sacred laws, time symmetry, the idea that physical processes should look the same running forward or backward. Normal crystals like diamonds or salt break spatial symmetry with their orderly atomic lattices. Time crystals shatter temporal symmetry, oscillating between states with a rigidity that seems to mock entropy itself. But here's the holographic twist. What if these temporal oddities aren't just in the universe but artifacts of its projection? They're endless cycles echoing from quantum computations on the boundary. Picture a clock that ticks forever without winding. Impossible, right? Yet time crystals achieve this by leveraging quantum entanglement, the same spooky connections that might stitch spacetime together holographically. In a lab, physicists create them by trapping ions or spin systems in a delicate dance, using laser pulses to kick them into a rhythm that persists long after the nudging stops. It's like striking a bell once and hearing it ring with perfect, undiminished tones for eternity. This isn't magic, it's a loophole where quantum coherence shields the system from decay, locking it into a meta-stable groove outside thermodynamics' grasp. Now imagine this phenomenon scaled to cosmic proportions. If the universe is a hologram, its boundary isn't static. It's a dynamic processor, updating spacetime's projection through quantum operations. Time crystals could be glimmers of that underlying rhythm, their temporal patterns mirroring cycles in the boundaries code. Think of a vinyl record. The music isn't in the grooves, it's the needle's interpretation of them. Similarly, time crystals might be our needle catching the universe's temporal grooves, revealing the hologram's refresh rate. Their breaking of time symmetry could hint at something profound, that time itself isn't fundamental, but emergent from the boundary's irreducible ticking. The implications ripple into black hole physics. Near a black hole's horizon, time appears to freeze from an outsider's perspective, yet quantum effects like Hawking radiation suggest activity continues. Time crystals model this paradox beautifully, their perpetual oscillations persisting even in equilibrium, as if encoding two timelines at once. Holographically, this duality might reflect the boundary's dual role, storing past states while computing future ones, like a cosmic DVR simultaneously recording and playing back reality. The wildest possibility, if time crystals are holographic artifacts, they could be nature's way of debugging entropy. Just as error-correcting codes protect quantum computers from decoherence, time crystals' unbreakable rhythms might stabilize the projection against cosmic crashes. Every tick could be a checksum, ensuring the universe's code runs smoothly toward whatever, or whenever, comes next. Every digital image has a limit. Zoom in far enough and crisp edges dissolve into blurry pixels. Could reality itself have the same fundamental resolution? The holographic principle hints that spacetime might not be infinitely divisible, that beyond a certain scale, the universe stops being smooth and instead reveals a granular underpinning, like a cosmic canvas woven from the tiniest possible threads. This ultimate resolution isn't arbitrary. It's tied to the Planck length, an astonishingly small measurement about 1/trillionth of a trillionth the width of an atom, where the classical notions of space and time break down into quantum foam. Picture a vintage video game like Minecraft. From a distance, its blocky landscapes appear textured and varied, but get too close and the illusion shatters. You're just staring at chunky, indivisible cubes. The holographic universe might operate similarly, with spacetime itself pixelated at the Planck scale. These pixels aren't empty, though. They're thought to flicker with quantum fluctuations, tiny eruptions where particles and antiparticles spontaneously emerge and annihilate in a frenzied dance. In this view, the vacuum of space isn't serene emptiness, it's a seething, pixelated static. Its resolution too fine for any microscope to capture directly. Why can't we zoom further? The same physics that suggests this granularity also prevents us from observing it. To probe the Planck scale, you'd need a particle accelerator the size of a galaxy, packing enough energy to distort spacetime itself. It's like trying to measure a single pixel on your phone screen. By hitting it with a sledgehammer, the tool you'd need to detect it would destroy the very thing you're studying. This isn't just a technological hurdle, it's a cosmic speed limit hardwired into the universe's code. The holographic twist, these pixels might not even be three-dimensional. If reality is projected from a two-dimensional boundary, then the Planck scale graininess we're imagining could be a shadow of something even stranger, a density limit on the universe's outer shell. Imagine a DVD storing a high-definition movie. No matter how advanced the player, you can't extract detail that wasn't encoded in the disk's microscopic pits. Similarly, the boundary's finite information capacity could set an unbreakable resolution for the projected cosmos, ensuring no detail gets rendered smaller than a Planck-sized dot. Gaming offers another parallel, a level of detail systems, where distant objects are rendered with lower resolution to save processing power. The universe might employ a similar optimization. At human scales, spacetime appears smooth because our observations don't require Planck resolution rendering. But for a hypothetical creature the size of a quark, reality might look jagged and pixelated, like a speedrunner glitching through a game's low-res backdrops. This isn't just speculation. Certain quantum gravity models predict that high-energy particles, like cosmic rays, could stutter as they travel, their paths subtly affected by spacetime's underlying graininess. The implications ripple into the nature of reality itself. If the universe has a maximum resolution, then Zeno's ancient paradox where space is infinitely divisible was wrong. You can't forever have the distance between 2 points because eventually you'd hit a pixel wall. Motion then isn't perfectly continuous, but a rapid slideshow of Planck-sized snapshots, advancing at a frame rate so high it feels seamless. Even time, often imagined as a flowing river, might be a sequence of discrete quantum updates, like a flipbook animating existence 1 Planck second at a time. Could this pixelation ever be detected? Fermilab's holometer experiment tried, hunting for spacetime's quantum jitter with ultra-precise lasers. While results were inconclusive, future interferometers spanning kilometers or even orbiting in space might spot the telltale fuzz. Another clue could come from gamma-ray bursts. If high-energy photons interact with spacetime's graininess as they cross the cosmos, they might arrive slightly scrambled, their wavelengths bearing the fingerprints of a pixelated universe. The holographic resolution limit doesn't just redefine smallness, it reshapes what real means. If you could peer past the Planck scale, you wouldn't find smaller building blocks just static, like a TV screen tuned to a dead channel. The universe's pixels aren't things, they're the end of thingness, the final line where physics stops and the projector's glow begins. And that raises a chilling beauty. Reality's sharpness might just be an illusion, a rendering trick perfected over 13 billion years. Quantum computing already feels like science fiction, machines harnessing the spooky laws of quantum mechanics to solve problems in seconds that would take classical computers millennia. But what if today's quantum processors are just the crude prototypes of something far stranger? Enter holographic quantum computing, the idea that future machines might not just use quantum principles, but could actually mimic the universe's own holographic projection system to achieve near magical processing power. At first glance, this sounds impossible. Today's most advanced quantum computers, like Google's Sycamore or IBM's Condor, rely on qubits quantum bits that can be zeros, ones, or both simultaneously thanks to superposition. These machines excel at specific tasks like simulating molecular bonds or optimizing logistics, but they're fragile. Qubits decohere at the slightest disturbance, collapsing into ordinary bits like a house of cards in a breeze. Holographic quantum computing offers a radical workaround. Instead of painstakingly maintaining individual qubits, these theoretical systems would encode information in entangled quantum fields that behave like miniature versions of the universe's own boundary dynamics, where data isn't stored in isolated points but smeared across interconnected surfaces like cosmic dry erase boards. D-Wave, the controversial pioneer of quantum annealing, has already stumbled toward this future. Their machines don't use traditional qubits but quantum flux processors that exploit entanglement across thousands of superconducting loops. While not full general-purpose quantum computers, these devices exhibit eerie holographic tendencies. In recent experiments, D-Wave processors solved optimization problems by evolving their quantum states similarly to how information propagates across a black hole's event horizon. not through step-by-step calculations, but through emergent, self-organizing patterns. It's as if the hardware were unconsciously mirroring the universe's own information processing playbook, where answers don't need to be computed so much as unfolded from underlying quantum relationships. The potential is mind-blowing. A true holographic quantum computer could tackle problems that stymie even conventional quantum machines, like simulating the birth of spacetime itself or modeling high-temperature superconductivity. How? By encoding data in quantum fields that behave like Maldacena's boundary, where calculations wouldn't be limited by the processor's physical size. Just as a hologram can reconstruct a 3D image from a 2D surface, a holographic quantum computer might simulate a million-dimensional system using only a few entangled layers of quantum material. Researchers at MIT and Stanford are already exploring quantum tensor networks, mathematical structures that mimic ADS/CFT correspondence, to design chips where information flows along holographic pathways, potentially sidestepping decoherence altogether. Critics argue we're centuries from such tech, but the universe itself is proof that holographic processing works. After all, our reality runs on it. Every black hole is a natural quantum computer, relentlessly crunching information on its horizon. Every particle collision in the Large Hadron Collider is a fleeting holographic calculation, playing out on the boundary of some higher dimensional space. The challenge isn't whether holographic computing is possible, but how to pry open nature's toolbox without breaking the cosmic copyright. The most tantalizing clue might come from an unexpected place: quantum error correction. Today's qubits fail constantly, but topological quantum computing, a promising approach using braided anyons, stores information in global properties that resist local noise, much like how holograms preserve images even if pieces go missing. This isn't just engineering, it's physics whispering that the universe's most stable information isn't stored in things, but between them, woven into relationships that transcend individual components. Future quantum machines might not look like supercomputers at all, but more like cosmic looms, threading reality's fabric one entangled connection at a time. So don't just imagine quantum supremacy. Picture holographic supremacy, where the computer isn't just in the universe, but of it, tapping into the same primal code that renders spacetime itself. When that day comes, we won't just be building machines, we'll be booting up baby universes. The universe's grand architecture isn't random, it's a cosmic tapestry of galaxies strung along vast filaments, weaving through voids in a structure so immense it defies earthly scales. This cosmic web, stretching billions of light years, resembles neurons in a brain, their delicate branches tracing patterns eerily familiar. But what if these filaments aren't just structures? What if they're holographic echoes, a three-dimensional printout of quantum data flickering on the universe's two-dimensional edge? Picture the cosmic web as a fractal lung, delicate, branching, breathing with the rhythm of dark matter and gravity. Each galactic cluster sits at the intersection of these threads like beads on an invisible necklace. Now zoom out, way out. From enough distance, the web structure mirrors something unexpected. The neural networks inside your skull. The resemblance is uncanny. Both systems maximize connectivity with minimal energy. Both evolve through self-organizing principles, and both seem to balance chaos and order in a dance of exquisite complexity. Coincidence? The holographic principle whispers, maybe not. If the universe is a projection, then the cosmic web could be its most visible artifact, a shadow cast by quantum entanglement patterns on the boundary. Think of it like a cosmic etch-a-sketch. The boundary's quantum bits encode the universe's blueprint, and as the projection unfolds, those entangled connections manifest as gravitational wells, pulling matter into filaments and nodes. The voids between, they're not empty, they're the negative space where the boundary's code dictates less density, like unlit pixels on a screen. This idea isn't just poetic. Simulations of holographic universes show filamentary structures emerging naturally from boundary dynamics, no dark matter required. In one radical model, the cosmic web's filaments aren't shaped by gravity alone, they're entanglement highways, pathways where quantum correlations on the boundary translate into gravitational scaffolding in the bulk. It's as if the universe is solving its own optimization problem, arranging galaxies along quantum threads the way ants follow pheromone trails. The neural network comparison deepens when you consider information flow. Your brain's neurons fire in synchronized patterns, creating thought. The cosmic web's galaxies move in coherent flows as if responding to some hidden rhythm. In 2014, astronomers discovered the dark flow, clusters of galaxies drifting en masse toward an unseen attractor. Holographically, this could be a glitch in the projection, a gravitational tug from a quantum fluctuation on the boundary, like a finger smudging the universe's lens. The most haunting implication: if the cosmic web is holographic, then its structure isn't just a relic of the Big Bang, it's a living, evolving dataset. Every galactic collision, every star's birth, every black hole's merger updates the boundaries code, subtly rewiring the universe's neural network. We're not just observers of this cosmic brain. We're its synapses firing in the darkness, stitching meaning into the void. When LIGO first detected gravitational waves in 2015, ripples in spacetime from colliding black holes over 1 billion light-years away, it didn't just confirm Einstein's prediction, it cracked open a new window to test the holographic universe. These waves, stretching and compressing spacetime like ripples on a pond, might carry faint anomalies in their waveform, subtle jitters betraying the pixelated code beneath reality's smooth surface. Think of it like streaming a high-def movie over a shaky internet connection. Most of the time, the video plays smoothly, but every so often, the image stutters or blurs, a telltale sign of the digital machinery underneath. In the same way as gravitational waves traverse the cosmos, they could interact with spacetime's hypothetical granularity, picking up tiny deviations from classical relativity's predictions. These glitches wouldn't be random noise, they'd follow distinct statistical patterns, like a cosmic barcode revealing the universe's resolution limit. The math behind this is staggering. In a holographic framework, spacetime isn't perfectly smooth. It's a lattice of Planck-scale pixels, each a quantum bit on the boundary. Just as sound waves distort when passing through a grid, gravitational waves traveling through this pixelated substrate should develop minuscule distortions, a phenomenon called modified dispersion. LIGO current precision isn't quite fine enough to spot these anomalies, but next-generation detectors like the Einstein telescope or space-based LISA could. Imagine tuning a radio to a new frequency and suddenly hearing whispers from the edge of reality. That's what these upgrades might achieve. Black hole mergers are the ultimate testbed. When two black holes spiral toward collision, their gravitational waves encode intricate details about spacetime structure. Simulations of holographic universes suggest these waves should exhibit faint echoes, reverberations caused by quantum fluctuations near the event horizons, like sound bouncing off unseen walls. In 2017, a controversial study claimed to find such echoes in LIGO data, though the results remain debated. Future detections with higher sensitivity could settle the question, turning black holes into cosmic laboratories for holography. But why stop at gravitational waves, pulsars ultra-dense, spinning neutron stars that beam radio waves like lighthouses, are nature's precision clocks? As gravitational waves pass through them, they subtly alter the pulsar's rhythms. Projects like NanoGrav monitor these beats for irregularities, hunting for a background hum of low-frequency gravitational waves. If spacetime is holographic, this hum might carry a unique statistical signature, like static from the boundary's quantum computations bleeding into the projection. The most tantalizing possibility, these experiments might not just test holography, they could reveal the universe's frame rate. Just as movies run at 24 frames per second to create fluid motion, the boundary might update spacetime's projection at a Planck scale refresh rate, too fast for any single experiment to catch. But the cumulative effect, a kind of spacetime screen tearing, visible in gravitational wave interference, could betray the cosmic rendering engine at work. We're on the verge of probing reality's source code, not through equations or philosophy, but by listening to the vibrations of black holes and neutron stars. Every gravitational wave is a messenger from the darkest corners of the cosmos, and if holography is right, they're whispering secrets about the two-dimensional surface where our reality is written. The next time LEGO lasers flicker, it might not just be detecting a collision. It could be reading the universe's deepest operating manual, one ripple at a time. If reality is a hologram, then everything we touch, see, and believe to be solid might be the grandest magic trick of all. An illusion so convincing we've mistaken it for the fabric of existence itself. Leonard Susskind, one of holography's founding minds, put it bluntly: the three-dimensional world is a kind of optical illusion. The real workings of the universe are happening on a distant, two-dimensional surface, and we're just shadows dancing in its light. This isn't just physics, it's philosophy with cosmic stakes, resurrecting ancient questions with terrifying new urgency. Are we, like Plato's cave dwellers, mistaking flickering projections for ultimate truth? Is the chair beneath you any more real than the pixels composing this video? The holographic principle doesn't just tweak our understanding of space and time, it erodes the very foundation of material reality. For centuries, science treated matter as the bedrock of existence. Atoms collided, stars ignited, and biology emerged from chemistry's dance. But if matter is a holographic projection, then what we call solid is just a particularly persuasive pattern in the cosmic code. Imagine pressing your hand against a wall. The resistance you feel, the warmth of the surface, none of it would be inherent to the wall itself, but a dynamic interplay of data points on the universe's edge, rendering tactile feedback in real time. This turns materialism on its head. The universe isn't a collection of things, it's a performance, a choreography of quantum relationships masquerading as substance. Critics push back fiercely. Physicist Joe Polchinski once quipped, "If the universe is a hologram, it's a damn good one." His skepticism cuts to the heart of the issue. Why does the illusion feel so seamless? Why does the hologram include the ache of stubbed toes or the sting of heartbreak? Holography's defenders counter that evolution shaped us to navigate the projection, not to perceive its edges. A video game character doesn't question the physics engine, it simply jumps when the player presses a button. In this view, free will might be another elegant fiction, our choices mere reflections of boundary computations unfolding light years away. The existential vertigo deepens when we consider identity. If the self is just a localized knot in the holographic weave, what happens to consciousness? Eastern philosophies like Buddhism have long argued that the I is an illusion, a temporary confluence of sensations and thoughts. Holography gives this ancient intuition a scientific veneer. Your sense of being a continuous, unified self could be the universe's most intimate rendering trick, a real-time montage of quantum updates convincing you that you persist from moment to moment. Yet for all its mind-bending implications, holography offers a strange comfort. If the universe is fundamentally information, then we're not insignificant specks in a vast, uncaring void, we're active participants in reality's unfolding story. Every observation, every measurement might be a collaboration with the cosmic code, a way the universe learns about itself. As Susskind once mused, the boundary isn't just out there, it's what out there even means. So where does that leave us? Not in a cold, simulated void, but in a universe more interconnected and alive with meaning than we ever imagined. The holographic principle doesn't diminish reality, it reveals its deepest magic. The chair beneath you may be an illusion, but the wonder you feel, that's as real as the cosmos gets. From black holes encoding cosmic histories on their surfaces to the eerie possibility that our entire universe might be a projected echo from some distant two-dimensional edge, we've journeyed through 30 theories that don't just bend reality, they shatter it. We've seen how entanglement could stitch spacetime together with invisible quantum threads, how dark matter might be nothing more than gravitational static from the universe's rendering process, and even how your own consciousness could be part of the cosmic code, a flickering subroutine in a holographic program larger than imagination. Each of these ideas peels back another layer of the illusion, revealing a cosmos far stranger and more interconnected than we ever dared to believe. But here's the kicker, these aren't wild guesses. They're grounded in cutting-edge math, from Maldacena's boundary-bending equations to the haunting precision of Bekenstein's entropy limits. The holographic principle isn't fringe science, it's a frontier, a lens that transforms everything from the tiniest Planck-scale pixel to the vast cosmic web into pieces of the same grand puzzle. Even the contradictions like quantum mechanics and relativity's bitter feud start to look like two sides of a holographic coin, both true because both are shadows of a deeper truth written on the edge of existence. So where does that leave us, staring into a mirror that reflects more than just light? If the universe is a hologram, then every star, every atom, every thought you've ever had is part of the projection. You're not just in the universe, you're of it, a three-dimensional ripple in a two-dimensional sea. That changes everything. The boundaries between you and the cosmos blur. The chair you're sitting on, the screen in front of you, even the time ticking away, none of it is solid in the way we assumed. It's all data dancing. Now it's your turn. If reality is a hologram, what does that make you? A glitch in the matrix, a conscious subroutine, or something even weirder? Drop your wildest thoughts in the comments below, and if your brain isn't completely melted yet, hit subscribe. We're just scratching the surface of the universe's deepest mysteries, and the next revelation might rewrite reality all over.